Yeah, then let's jump into it. It is about LINSTOR, DRBD, and how all that plays together with CloudStack. So my plan was that I start at 0, try to tell you all the story, and then the updates come in the last part of the presentation. So I don't lose those who have no clue about what I'm talking here. So the challenge we are solving is you have a bunch of machines that has built-in storage devices, and you need to have cloud storage. So this is the part what LINBIT is solving. And the software we're doing that comes in layers that are strictly separated, each doing its own job. So let's start with LINSTOR, that is from the higher level. So here on this slide, at the top, you see CloudStack, and maybe there are some other cloud things we interact with, but today we're only talking about CloudStack. So when I go from top to bottom, right, so we have a driver in CloudStack. I think it's called a LINSTOR driver in CloudStack that uses the REST API to talk to the controller. The controller is like the central part of the storage software. You have one instance running in the cluster, so that's very comparable to the CloudStack manager, right? You have one instance running, controlling everything. On each node that either consumes storage or has storage devices, we have a LINSTOR satellite running. So you could call that node agent. Maybe the difference is then the satellite is completely stateless and configurationless. So it's the controller that establishes the connections to the satellites. The controller, you usually have that set up in a HA way, so it has at least 3 home locations where it can run, and it moves between these locations if one of its machines fail, or you you trigger a switchover because you're planning to do maintenance on one of those nodes. And yeah, what is the satellite doing? It either controls LVM, so it uses this LV create command and all its friends, or it uses the CFS commands if you want to use ZFS to manage the local storage in your machines. And yeah, and apart from creating logic volumes, it also configures DRBD to establish the actual virtual volumes. So this is the very high level view of the architecture, and the control structure we see here in place, that's only used for the control operations like creating a volume, taking a snapshot, resizing a volume, things like that. That's not the data path. And let's look at it with a few examples. So let's say we have a 6-node cluster. Each of those nodes has enough CPU and memory to run the actual workload, and each node has built-in storage devices. So if we get from CloudStack, I want to create here a new virtual machine. And let's assume that our resource group, so that's the equivalent to a primary storage in CloudStack, has the policy that each of the virtual volumes should be two-way redundant in order to survive node failures or storage device failures, right? So then LINSTOR would create one of the replicas co-located with the VM and one replica somewhere else. That's the small same for the black VM, right? We have one replica co-located. And this co-locating one replica with the actual workload, that is a huge advantage. Because when we read anything from the virtual volume, we can read it from the local replica. We don't add network latency to it. We don't create bandwidth we don't create load on the network. So 2 advantages: faster access, lighter load on the network. Writes, well, for writes we need to go over the network, obviously. Yeah, and the driver, when you create new VMs, it always tries to co-locate one replica, if possible, right? If the storage devices in this node are already fully utilized, well, then it needs to go somewhere else, obviously. Now, it might happen that you do a live migration of a VM. It might happen that you migrate it to somewhere where we don't have a local replica of that virtual volume. So no problem. That is, of course, supported. And then it's in the, I would call it a non-optimal state. So it has to fulfill read requests by going over the network. My example here is about a hyperconverged architecture. So in that case, you could configure LINSTOR that after a certain time it runs in this configuration, it tries to migrate one of the replicas to the node where it gets accessed. You can set that to 60 minutes, to 1 minute, to 10 days, whatever you like, right? And now let's assume on the node where the black VM is running is enough storage available. Then it does all these changes, it puts it into the DRBD config, DRBD resyncs the data, so it copies over all the blocks, and all that happens completely transparent to the VM, right? The VM is running all the time. And after this resyncing is finished, it would remove the third replica because the policy for this primary storage says 2 replicas, not 3. Okay, that was LINSTOR by example. I hope that was easy to follow. Now I'm going deeper down in the stack to DRBD. So DRBD is the component that does the actual data access. So that's a driver in the Linux kernel, and I come to that. Now let's start on the high level for the low level component. It provides you with virtual block devices. So you see it on your Linux box. If you go into the dev directory, you see dev DRBD 1000, dev DRBD 1001, and so on. In the moment you open such a device for reading and writing, it changes its role. It becomes a primary. It always replicates from primary to secondary. Moving an application around is pretty easy. You stop accessing it here. A moment later, you can start accessing it there. If you follow me, at this point, you can say, oh, what's about live migration? So in live migration, what happens is that QEMU and KVM are instructed to do a live migrate. So it actually opens it on the target host of the migration first. Then it moves over all the memory pages. And after that is finished, the QEMU stops on the source node. So in this process, it's dual primary for a short amount of time while the live migration is running. But our driver handles all that. It puts DRBD into dual primary mode, does the live migration. After the live migration, it disables this dual primary mode. Here, DRBD can also replicate multiple volumes within it's called consistency group. So that means you could have different storage types, let's say rotating media and NVMe SSDs, and you have an application like an Oracle database running in a VM. You have both storage types exposed into the VM, and you put the table spaces of the database onto the slow storage and the write-ahead log on the fast storage. If you do something like that, you need to make sure that mirroring these two volumes is always consistent in itself. Otherwise, the write-ahead log and the table spaces are not in sync. So, long story short, it's capable of doing that. And yes, it's not very often used in the wild. Then DRBD is not a two-node technology. It can mirror to multiple secondaries concurrently, and each of the replication links might be synchronous or asynchronous, so same data center or somewhere else. You can also switch that at runtime. Then let's go on to the diskless mode of operation. So DRBD can also give you access to one of a virtual volume on a node where we don't have a local replica of it. So we already had that in the example with the live migration. DRBD will shield you from I/O errors as long as possible. So let's assume in this example, let's assume we have a QEMU process running on top of on the primary node. It sends down a read request. DRBD might send a read request to the upper secondary, and that node fails before it answers the read request. What then happens is that the primary says, oh, where's my answer? It's not coming. I request it from the other secondary. It gets the data from there. It finishes the I/O request. So your application in the VM never saw an I/O error, although we had a node failing during the I/O operation. If that failed node comes back, it's automatically reintegrated, and reintegration means that all the data blocks that were changed in the meantime are resynced over to the node that was away for a little bit. And only after that resync is finished, it's completely integrated and ready to take read requests again. And here is another illustration showing where that sits in the stack. So here on this illustration, we have only two machines, and the orange box, yes, it's visible on the beamer. The orange box is the Linux kernel, and we have the so-called I/O stack, so usually a file system, well, in case of virtualization. And the way we integrate into Apache CloudStack, there won't be a file system. So we have the buffer cache, and then DRBD inserts itself into the stack at this position, the disk scheduler, and then the driver software and the hardware. So it mirrors out everything since it is in the I/O path, and it completes write requests only after they have written on both sides. So it waits for the acknowledgement to travel back from the other side. That's the so-called synchronous mirroring, and that's the default mode. And this is what you would use if you use it within a data center. It's also capable of doing remote mirroring, right, to another data center, long distance, long latencies. Then you would run it in asynchronous mode. That's fully part of the solution. Okay, so this is my, one more slide. Where is it a fit? So it fits a lot with I/O demanding workloads. So many of our customers run all kinds of databases, either transactional databases or analytical databases, all the databases you know. And with that, it is a good fit for any application that is I/O demanding. In other words, it's faster than Ceph, a lot. So every few weeks, we get the message, oh, we love Linbit, it's 3 times faster than Ceph on the same hardware, 6 times, whatever. Okay, then let's switch to the second part of my presentation. Where are we? What are the updates, right? So we started our CloudStack journey in 2021. And there we have is, and this bar chart gives you the number of commits to the CloudStack, to the LINSTOR driver in CloudStack. So we started in 2001, and the initial commit was a big one. the driver. And soon after that, I hope you can read that, the green numbers at the bottom, that's the CloudStack releases. So that was short before the 4.16 release. So that was the first CloudStack release that had the LINSTOR driver. And I think that was the CloudStack collaboration conference in Sofia, where I did my first presentation. So the people were so, oh, a new thing, right? Adoption started slow. But after some time, the POCs probably turned into real things, and we got demanding customers and demanding workloads. And you see this peak around last year in 24, where probably the missing features were added, the remaining bugs were closed, etc. But what for me is the important thing on this chart is it's going down again. So it's becoming to get boring, right? And when it becomes boring for the developers, that's a good sign for those guys who don't want to develop it but use it, right? So that's my message with this graph. It's getting a bit boring, but we are not at the end of the story now. So we have a few plans for the CloudStack integration. And what the driver does up to now is the usual stuff. So you can create volumes, you can resize them, take snapshots, and all the operations, sorry. But what's not in yet is that you can do online migrations between different primary storages. And there are 3 cases we need to look at. And one is, you might have one LINSTOR cluster, so one LINSTOR controller, and different resource groups. And a resource group, that's a LINSTOR term, but it basically is your storage policy setting. So that could be something like 2-way replicated, or 3-way replicated, or 2-way replicated plus 1 replica needs to be in this data center and the other replica needs to be in that data center. So all these different kinds of policies we express as different resource group. Each resource group maps to one primary storage in CloudStack. So, but when you have a few of those different policy sets, you might want to move the storage of one VM from one policy set to the other. So actually the data stays in the same locations, but from the point of view of CloudStack, it's, oh my God, it moves from one primary storage to another. That's a huge thing. So this is something we need to express in the driver, in the code, and make possible that those migrations you can do through the CloudStack management interface, but in the end, the data doesn't move, right? So that's the first of the 3 cases here. Then, and I think we will also implement it in that order. The next complexity is if you have multiple LINSTOR clusters behind your CloudStack, to be able to online migrate the storage of a running VM between those. And then the third one, the final challenge, is to allow the users to online migrate off their NFS primary storage onto LINSTOR. So these are the big plans. Maybe we get another bump in the curve, but then for a good reason, not because we are fixing bugs, because we are adding another huge thing. Or maybe it doesn't produce a bump because it's well tested as single commit and doesn't show up there. Okay, so that's the roadmap for the integration in CloudStack. And not only our CloudStack integration has a roadmap, also LINSTOR. So that's the orchestrator that manages these storage clusters. So right now, we have a number of customers and even more installations that are in the area of hundreds of machines. Some of them disaggregated, so only 20 storage servers plus hundreds of compute servers. Some of them are completely HCI, so 300 nodes that have storage built in plus run VMs. We don't have an installation with thousands of machines, and that has a reason. That's scalability of LINSTOR is not there yet. So hundreds, no problem. 200, 300, 400, this is where it scales at the moment. And our customers are driving us, so of course we're working on that. So one example in one of the recent releases, we tested this restarting of a satellite component when there are 1,000 resources on the machine. So 1,000 virtual volumes and active snapshots, etc. And when we started the optimization, it took 2 minutes to get this component up and running again. And now we're down at 8 seconds after a little bit of work. So that was good. So another recent achievement was this, the master passphrase. So if you have encrypted volumes, the solution leverages on looks, de-encrypt to do the actual encryption. And each encrypted volume gets a different passphrase. And all those passphrases are encrypted by a master passphrase. And where do you put this master passphrase, right? You don't want to put it into a config file. So we have now the possibility to put it into the TPM chip on the motherboard. So this is where it should be. This is a good location for such a information. Yeah, and on the roadmap is various details about balancing resources. So that means moving replicas to other hosts in a clever way. So that's roadmap items. And the scalability work, that continues, of course, right? So I want that when I show up here in a year, maybe it takes 2, I don't know, I can tell you, okay, we have our first installation with 1,000 nodes. But let's see. Also the gods of the market needs to be in. Okay, the other important component, that's DRBD, the kernel driver. So also that is moving along. So recent changes, that's really very recent. It has, in order to do efficient resyncs when one host goes down, it has a change tracking bitmap in its metadata. And this change tracking bitmap is also in memory. And when you have machines with a lot of storage, so think in the many hundred terabytes to petabytes attached to a single machine, then the size of this bitmap begin to matter. And for 25 years, it was fixed that 1 bit in the bitmap represents 4 kilobytes of storage. That's a fine granularity, it's good. But when you attach huge amounts of storage to a machine, this begins to matter. So we considered, okay, when we reduce the granularity, or in other words, increase the bitmap blocks, we save a lot of memory. And this illustration is 4:1, right? You see it. It's a lot smaller. And of course, it gets a little bit coarse-grained. So that means A resync has to resync a few blocks more, but probably the trade-off works in lots of cases. Another recent achievement was the resync without replication. When we need to do a resync operation, we have an active workload running. So suddenly we have not only the I/O bandwidth of the active workload, but like a second I/O stream going from one node to the other node. And it turned out for some workloads it makes sense to not do that in parallel, but let the resync only resync the changed blocks and let the active workload write and read. And then it creates markings again, dirty markings. And then we do the resync a few times. And the interesting finding was that for most workloads, this new strategy results in a quicker resync. That's a little bit counterintuitive, and I don't have enough time to explain all that. It would be a nice academic paper. Other things, zero copy receive for our TCP transport that will probably come pretty soon, and also using in-kernel compound page allocations for huge IOs. And the support for multi-data stuff is also ongoing. So that's what's happening on the DRBD side. Okay, I only have a few minutes left, so let's go over the summary real quick. So there are 4 takeaways for you to remember. One is LINSTOR is about keeping data redundant, so protecting data. CloudStack has the HA mode. It will keep your services running. All what we do is open source, just as CloudStack. So this is a platform you can bet on, and it has the best performance. That's it. Here's the survey slide, and